is Kirsten Masana, and this is Lab 1 Constant Velocity for Physics 2211. The purpose of the lab is to observe the motion of an object that is moving at a constant speed without changing directions. We will analyze our observed model from our video using Tracker and compare it to our computational model computed through GlowScript. Fundamental physics principles. Newton's first law states that an object in motion will stay in motion unless acted on by an external force. This law demonstrates that an object in motion does not need an additional force to keep it moving. Next, we have Newton's second law, which states that the net force acting on a system is equal to the rate of change of its momentum with respect to time. Using this concept is vital in understanding the relationship between net force and constant velocity. On the right here, we have a free body diagram, which shows the magnitude and direction of all external forces acting on a system. If all these forces are equal to each other, they cancel out and create a constant velocity motion because F net is equal to 0. However, if one of these forces is stronger than the others, there will be a net force leading to changes in momentum and a non-constant velocity. Next, we have Newton's second law, which is F net is equal to dp dt. We do some rearrangements to get the momentum update formula, and we divide this whole thing by mass to get the velocity update formula. If we set net force is equal to 0, we're left with V final is equal to V initial, which is constant velocity motion. Here are important equations that will be used throughout this lab. We have the position update formula, where if you know the initial position and the average velocity, you can predict what the final position will be sometime later. Then we have the velocity update formula, where if you know F net, mass, and initial velocity, you can predict what the velocity will be sometime later. System is what we're studying, which is the object role in the video. Surrounding is everything else. This could be table, gravity, normal force, friction. Some assumptions that we're making in this experiment is that there is no friction, we're ignoring air resistance, and there is no external forces acting on the object. Now we're going to get into the details of the experiment. Here's a video of an object that is moved across the screen with a constant velocity motion. The purple axis establishes the coordinate system, and the blue line represents the calibration stick to set the scale. As the video plays frame by frame, the position and the time of the object are placed into the chart here. This then leads us to our next slide, where I placed all the data into an Excel spreadsheet, and from here we can calculate all the unknowns needed to create a computational model. First, we have our time is equal to 0, our position is equal to 0. We find delta t by taking the change in time between two measurements. Then our next step is to calculate the initial velocity. We do this by V average is equal to the change in displacement over the change in time. Then we plug everything in and we get an initial velocity of 0.7425. Using our calculations from the previous slide, we can set up initial conditions, which is the position of the ball, the initial velocity, and the change in time. We can then use a while loop to apply repeatedly Newton's second law. At line 56, we set our net force equal to 0 because we are observing a constant velocity motion. At line 61, we use the velocity update formula, and as mentioned prior, this is equal to 0, so we are left with V final is equal to V initial. At line 65, we use the position update formula, which is final position is equal to initial position plus velocity times delta t. Then we can run our program. And after running our program, we have computed values for time and position of the object with constant velocity that can be placed into an Excel spreadsheet as well. Now, taking the tables from the observed and predicted motion, we can create a graph and compare. The orange is the predicted from the computational model, and the blue is the observed from the video. Now, they both have a positive slope demonstrating a constant velocity motion in a positive x direction. At the beginning, the lines stay pretty similar. However, by the end, the observed line begins to deviate from the computational model. This is because in our real-life scenario from the video, the object has external forces such as gravity and friction acting on it, while the computational model maintains a constant velocity throughout the entire time interval. Regarding possible sources of error, there could be human error when plotting points of position in Tracker, and it is possible that the calibration defined in Tracker was not perfect. What if? What if we flip the x-axis? If we were to redefine the coordinate system, the value of the position and velocity would remain the same, but the values would become negative since the object is now traveling in the opposite direction. This would make the slope negative. Remember that the position and velocity are vectors, so they have both magnitude and direction. What does this mean? Is it possible to say how many pushes and pulls are being added together to give 0 net force in the case that you observed? It would be difficult to say exactly all the pushes and pulls acting on our system because there are so many forces at play here, making it too difficult to detect and measure all forces that contribute to the equation, especially since everything in the surroundings is exerting gravitational force on each other and the system. Thank you.